Welcome to the most expensive geology lesson you'll ever take. Today, we're diving deep, and I mean really deep, into the story of diamonds. And no, I'm not talking about your ex's promises. I'm talking about actual diamonds that traveled 200 kilometers from Earth's mantle just to end up on someone's finger. Here's the thing. Diamonds aren't made in your neighborhood. They're not even made in the crust where we live. They're immigrants, fancy foreigners from the deep mantle who hitched a ride on what I like to call Earth's most violent elevator service. Think of Kimberlite volcanoes as the FedEx of the geological world, except they only deliver to the surface once every few million years. And the shipping fees? Well, let's just say they're measured in billions of dollars and decades of work. So buckle up, because we're about to explore how these sparkly little carbon crystals form, how geologists play detective to find them, and why mining them requires the kind of extreme engineering that makes building a skyscraper look like playing with Lego. Let's get one thing straight right off the bat. Kimberlite doesn't make diamonds. Kimberlite is just the Uber driver. The diamond is the passenger who's desperately trying to get to the surface before it turns into graphite. Yes, pencil lead. Same element, very different resume. Look at this diagram. Down there at 140 to 200 kilometers deep, where temperatures hit 900 to 1300 degrees Celsius and pressure is crushing, literally 45 to 60 kilobars of sit-down-and-stay carbon. That's where diamonds are born. That's the diamond stability field, the VIP lounge of the mantle. Now here's the catch. If this kimberlite magma takes its sweet time getting to the surface, stops for a coffee break, checks its phone, the diamond says, "You know what? This pressure is gone. I'm just going to relax and become graphite." And poof, there goes your engagement ring. But if the kimberlite rockets upward at meters per second, and we're talking NASCAR speeds in geological terms, the diamond gets flash frozen at the surface before it can decompose. Rapid cooling is the hero of this story. Remember, kimberlite equals carrier rock. Diamond equals foreign passenger. The kimberlite is not the factory. It's the high-speed elevator that saved the diamond's life. All right, let's talk about what a kimberlite pipe actually looks like. And no, it's not a pipe you smoke. It's shaped like a giant carrot buried upside down in the earth. Or maybe an ice cream cone that decided to stage a rebellion. There are three zones to this geological oddity. First, at the top, you've got the crater zone. This is the aftermath of the party, filled with volcanic debris and lake sediments. Basically, the hangover. Then comes the diatreme zone, which is my favorite because it sounds like a rejected Transformers character. This zone is brecciated. That's geologist speak for blown to smithereens. When CO2 and water-rich magma came screaming up from the deep, gases expanded explosively, fragmenting everything in sight. Imagine a champagne bottle if it held geological rage instead of bubbly. Finally, at the bottom, there's the root zone, also called the hypabyssal zone. This is where the kimberlite is still crystalline and unfragmented, the calm before the storm. Here's how it forms. Deep underground, you get partial melting. CO2 and water create this volatile-rich magma. Then, boom, explosive ascent. Gas expansion drives the whole thing upward like a rocket. The eruption fractures the crust, excavates a giant hole, and creates this carrot-shaped pipe. It's violent. It's fast. It's the geological equivalent of a mic drop. Pop quiz. Where do you find diamonds? If you said everywhere, congratulations, you're wrong. If you said ancient cratons, give yourself a gold star and a metaphorical high five. Diamonds don't just pop up anywhere. They need special conditions, and those conditions exist almost exclusively in cratons, the ancient, stable hearts of continents. These are the geological grandpas, the parts of the earth that have been sitting there, unmoved and unbothered, for over 1 billion years. There's even a rule about it. It's called Clifford's Rule, and it's not named after a big red dog. It states that economically viable diamond deposits are restricted to these thick, stable, lithospheric keels. Why? Because they provide the deep pressure required to keep diamonds from turning into graphite. Let's take a world tour. We've got Ekati and Diavik in Canada's Slave Craton, that's the frozen north. Then there's Mir and Udachnaya in Siberia's Craton, even more frozen. Down in southern Africa, we have Jwaneng and Venetia in the Kapval Craton, where it's hot and dry. And over in Australia, there's Argyle, which produced those famous pink diamonds before it closed. The point is, if you want to find diamonds, don't dig in your backyard. Head to the ancient cratons. They're the only places on Earth old and stable enough to host this geological treasure hunt. So you want to find a diamond mine. Great! Just go out and look for a kimberlite pipe. Easy, right? Wrong. Kimberlite pipes are tiny targets. We're talking geological needles in continental haystacks. But here's where geologists get clever. They don't look for the pipe directly. They look for the breadcrumbs. And by breadcrumbs, I mean something called indicator minerals. These are the heavy, weather-resistant minerals that erode out of the kimberlite pipe and get scattered downstream or down ice by rivers and glaciers. They're like geological clues in a really expensive treasure hunt. The main suspects? G10 pyrope garnet, shiny red gems that scream, "I came from the mantle." Then there's chrome diopside, which is green and equally talkative. And ilmenite, an iron titanium oxide that's basically the strong, silent type, but still tells you where to dig. Geologists sample soils in glacial till, looking for these pathfinders. When they find them, they trace the concentrations upstream or up ice, following the dispersal train like Hansel and Gretel. Except instead of a gingerbread house, they're hoping to find $1 billion diamond deposit. It's forensic geology at its finest. Follow the breadcrumbs, find the treasure. Okay, so you've followed your indicator minerals, and you think you found a kimberlite pipe. But before you start celebrating and ordering your private yacht, you need to verify. And that's where geophysics comes in, the CSI of the geology world. Kimberlites have distinctive geophysical signatures. They often show up as circular magnetic highs or lows, or as gravity lows, because they're less dense than the surrounding rock. It's like they're waving a flag saying, "Hey, weird stuff over here." But geophysics alone isn't enough. You need boots on the ground, or rather, drills in the ground. Drilling is required to define the exact shape of the pipe and to pull up fresh rock samples. This is expensive, nerve-wracking, and absolutely essential. Here's the moment of truth. You take that drill core and subject it to something called caustic fusion. You literally dissolve the rock in acid and heat to recover tiny micro-diamonds. If you find them, congratulations! Your pipe is diamondiferous, fancy word for it has diamonds. If you don't find diamonds, well, back to square one. And that, my friends, is why diamond exploration has a failure rate higher than a New Year's resolution to go to the gym. Let's talk money. Because at the end of the day, finding diamonds is one thing. Making money from them is a whole different beast. Here are the cold, hard facts. Fewer than 1% of kimberlite pipes are economically viable. That's a 99% failure rate. You've got better odds at a casino, and that's saying something. If you do hit the jackpot, here's what you're looking at. Over $1 billion USD just to build the mine. That's billion with a B, the kind of money that makes venture capitalists break out in a nervous sweat. Oh, and the timeline? 10 to 20 years from discovery to first production. So, if you're hoping for quick returns, maybe invest in something else, like Bitcoin or lottery tickets. And even after all that investment and waiting, your revenue depends on diamond price fluctuations, which are about as predictable as a cat's mood. One day prices are up, the next day they're down, and nobody really knows why. This is the economics of scarcity. High risk, high capital, long lead times, and volatile markets. It's not for the faint of heart, or the impatient. Let me introduce you to royalty. Jwaneng Mine in Botswana, affectionately known as the Prince of Mines. And honestly, it's more like the king. Located in southern Botswana on the Kapval Craton, Jwaneng is the world's richest diamond mine by value. Not by volume, by value. The diamonds that come out of here are so high quality that even with moderate grades, the mine prints money. The geology is fascinating. 3 separate kimberlite pipes, north, center, and south, coalesced into one massive deposit. It's like geological carpooling, and it worked out beautifully. Here's the secret to Jwaneng's success. Exceptional US dollars per carat. The diamonds are so good that they compensate for not having the highest quantity. Quality over quantity, baby. It's the Rolls-Royce of diamond mines. And the impact? This mine's revenue funds education and healthcare across Botswana. It's a global model for resource governance. Proof that when managed responsibly, natural resources can actually improve lives instead of just lining pockets. Jwaneng isn't just a mine. It's a national treasure. So how do you run the world's richest diamond mine? Very, very carefully. First up, geotechnical control. Jwaneng's kimberlite is weak and weathered, which means the pit walls could collapse if you're not paying attention. So they use slope radar to monitor wall stability 24/7. It's like having a geological babysitter that never sleeps. But here's the challenge. Open pit mining can only go so deep before it becomes physically and economically impossible. So Jwaneng is undergoing the transition, moving from open pit to underground block caving. This extends the mine's life and keeps the diamonds flowing. Block caving is ingenious but complex. Basically, you let the ore body collapse under its own weight in a controlled manner, and you collect the broken rock from below. It's like mining by inducing a very slow, very profitable avalanche. And the national impact? The revenue from Jwaneng funds schools, hospitals, and infrastructure. It's not just about extracting wealth, it's about creating wealth for an entire nation. This is engineering value, in every sense of the word. Now let's head north, way north, to the Northwest Territories of Canada, where the Ekati mine operates in conditions that can only be described as, why would anyone voluntarily work here? Ekati is built on the slave Craton, and it was discovered by tracing indicator minerals up ice through glacial till. Imagine following sparkly breadcrumbs through a frozen wasteland. That's dedication. The geology here is different from Jwaneng. Instead of one giant prize, Ekati is a portfolio operation. Over 150 kimberlite pipes, with about 10 of them economic. It's quantity over quality, the geological version of diversification. And the challenge? Operating in a remote, sub-zero glacial environment. We're talking temperatures that regularly hit -40 degrees Celsius, where exposed skin freezes in minutes, and machinery protests like a toddler at bedtime. But despite the brutal conditions, Ekati works. It was Canada's first diamond mine, the pioneer that proved you could find diamonds in the Arctic. It paved the way, literally and figuratively, for an entire northern diamond industry. Ekati is proof that when there's sparkle involved, humans will work anywhere. Let's recap the entire journey in one visual, because honestly, it's wild. It starts 140 to 200 kilometers deep in the mantle, where temperatures hit 900 to 1300 degrees Celsius. That's hot enough to melt your face off. Down there, carbon crystallizes into diamond under immense pressure. Then comes the high-speed elevator, kimberlite magma that rockets upward at meters per second. If it's fast enough, the diamond survives. If it's slow, you get graphite. Speed matters. At the surface, geologists play detective, tracing red pyrope garnets and black chromite upstream. They're following the breadcrumbs back to the volcanic pipe, which is shaped like a carrot buried in the crust. Once they find it, they dig. First with open pits, which can go hundreds of meters deep, but eventually they hit a limit and have to transition to underground mining, tunneling beneath the pit to chase the ore body deeper. And here's the kicker. After moving millions of tons of rock, most mines produce only 0.2 to 1.5 carats of diamond per ton. That's finding a needle in a haystack, if the haystack was the size of a mountain, and the needle was worth $5,000. From mantle to market, it's a journey defined by violence, science, and engineering. Operating Ekati is like running a mine on another planet. Except that planet is Earth, and it's just really, really cold. Let's talk logistics. Fuel, explosives, heavy machinery, none of that can be flown in. So how do they get supplies? Winter ice roads. For about 2 months every year, when the lakes freeze solid, they build roads on the ice and truck everything in. Miss that window, and you're out of luck until next year. Talk about pressure. Then there's the permafrost management. The ground is permanently frozen, which sounds stable until you realize that pit walls and waste dumps have to remain stable through freeze-thaw cycles. One wrong move, and you've got a geological disaster on your hands. And the cold? We're talking -40 degrees Celsius operations. That's the temperature where Celsius and Fahrenheit agree to both be miserable. Equipment breaks, batteries die, humans turn into popsicles if they're not careful. Ekati's strategy is lateral expansion, mining multiple medium-sized pipes instead of going ultra-deep on one. It's diversification through geology. This is extreme mining at its finest. If diamonds weren't so valuable, nobody would bother. But they are, so we do. Let's put our two case studies side by side, because the contrast is stunning. In one corner, we have Jwaneng in Botswana. Hot, arid, desert climate. The geology is a massive cluster, 3 pipes that merged into one geological jackpot. Discovery was done through soil sampling and magnetics. The strategy? Go deep. Transition underground and chase that high-value ore as far down as you can. In the other corner, Ekati in Canada. Arctic, glacial, frozen tundra. The geology is a portfolio. Many moderate pipes scattered across the landscape. Discovery was done by tracing minerals up ice through glacial till. The strategy? Go wide. Lateral expansion across multiple pipes. 2 completely different environments, 2 completely different approaches, but both work. It's a beautiful reminder that in geology, like in life, there's no one-size-fits-all solution. You adapt to what the earth gives you, whether that's blistering heat or bone-chilling cold. You make it work. Because at the end of the day, diamonds don't care about your comfort zone. So you've mined the Kimberlite. Congratulations. But you're not done. Now you have to extract the actual diamonds without destroying them. And that's harder than it sounds. Step 1. Comminution, which is just a fancy word for crushing. But here's the catch. You have to crush gently. Smash too hard and you'll break the diamonds. Crush too lightly and you won't liberate them from the host rock. It's a Goldilocks situation. Step 2. Dense media separation, or DMS. You use a heavy liquid to separate the dense diamonds from the lighter waste rock. Diamonds sink, garbage floats. Simple physics, big results. Step 3. X-ray transmission, or XRT. This is where technology gets cool. X-rays detect the atomic density of diamonds, and when they're identified, a puff of air ejects them from the conveyor belt. It's like a mechanical sneeze that only targets gemstones. Finally, recovery. Hand sorting, security, and making absolutely sure nothing gets stolen. Because at this point, you're handling millions of dollars of sparkle, and people get ideas. The goal of processing? Liberate the diamond from the host rock without breaking it. Treat it like the precious cargo it is. Let's talk about the future, because it's complicated. The technical challenge is clear. We're running out of easy diamonds. Surface deposits are being depleted, which means we have to go deeper. And deeper means more complex, more expensive underground methods like block caving. Block caving is brilliant. You let the ore body collapse under its own weight and collect the broken rock from below. But it requires serious engineering, massive infrastructure, and nerves of steel. The geological reality? Global diamond grades are declining. We're finding fewer high-quality deposits, which means exploration is getting more expensive and less successful. The low-hanging fruit is gone. But here's where it gets interesting. ESG commitment, environmental, social, and governance. Mining companies are now managing tailings, recycling water, over 80% at Jwaneng, and ensuring progressive reclamation. They're turning old mine sites back into green, habitable landscapes. This isn't just about digging up diamonds anymore. It's about doing it responsibly. It's about ensuring that when the last diamond is extracted, we leave behind something better than a giant hole in the ground. The future of diamond mining is about depth, difficulty, and stewardship. It's about doing the hard thing the right way. Here's the truth. Successful diamond mining is not luck. It's not stumbling onto a pile of sparkly rocks. It's the rigorous, relentless integration of multiple sciences working in perfect harmony. You need structural geology to understand how the Earth's crust is built and where ancient cratons hide. You need geochemistry to identify indicator minerals and trace them back to their source. You need geophysics to detect magnetic and gravity anomalies that hint at kimberlite pipes. And you need geotechnical engineering to safely dig a hole hundreds of meters deep without everything collapsing. It's geology, chemistry, physics, and engineering, all holding hands and singing Kumbaya while drilling through rock. From 200 kilometers deep in the mantle to the engagement ring on someone's finger, that journey is defined by violence, science, and engineering. It's one of the most extreme supply chains on Earth. So the next time you see a diamond, remember, that little sparkle traveled farther and endured more than most of us will in a lifetime. It survived volcanic explosions, geological detective work, billion-dollar investments, and extreme engineering. And that, my friends, is why diamonds are forever. Because getting them here in the first place was an absolute miracle. And that concludes our journey from mantle to market. I hope you now appreciate just how much science, sweat, and sheer determination goes into every single diamond. Remember, diamonds aren't just pretty rocks. They're geological time capsules, survivors of extreme violence, and products of human ingenuity at its finest. So whether you're admiring one in a jewelry store or studying them in a lab, you're looking at one of Earth's most incredible stories, written in carbon and delivered by Volcanic Express. Thank you for joining me on this sparkling adventure. Class dismissed. Now go impress someone with your newfound diamond knowledge.